All right. Welcome to Unit 15, Redox Reactions. So our first lesson deals with oxidation states, which we've actually already covered a little bit, but this whole chapter is based on oxidation states. So we are going to review it and talk a lot more about it. So in our redox reactions, and redox is short for oxidation reduction reaction, or, well, if you look at it the way redox is written, reduction oxidation reaction. You have a reaction occurring. Here we have A plus B, and they're going to form A positive and B negative. When that reaction occurs, we have a transfer of electrons. An electron is being transferred from A to B. You notice the charge up here above the reactant A is 0, and the charge above the reactant B is also 0, yet when they formed a product, A now has a positive charge. He has lost an electron, whereas B has a negative charge. B gained that electron. The electron didn't disappear, it didn't fly away, it transferred from A to B, and that's a redox reaction. Some terminology, make sure you guys are comfortable with this terminology. The species which loses an electron, in this case A, again A went from 0 to positive, that species is what we call oxidized. Now it's also known as the reducing agent because it does the reducing. In this case, B goes from 0 to -1. B gained an electron, and the species which gains an electron is known as the reduced species. We can say B was reduced. And similarly, B is called the oxidizing agent because it does the oxidizing. So we could say that B was reduced. We could also say that B was the oxidizing agent because it oxidized A. So there's a couple of different ways to say it. Make sure you guys take a look at this slide and get comfortable with the terminology. Something that always really helped me, and you hear me say it a lot, is the saying, Leo the lion goes grrr. So Leo stands for loss of electrons is oxidation. Loss electrons, oxidation. Leo the lion goes grrr. The grrr part, gain of electrons, is reduction. So gain, electrons, reduction. Which is kind of a helpful saying to help you remember that when you lose electrons, you're oxidized. When you gain electrons, you are reduced. All right, again, this should be a quick review about oxidation states. So anytime you have an uncombined element, an element by himself, the oxidation state is 0. So for example, F2, the oxidation state is 0. And yes, I did purposefully choose a diatomic to show you, hey, even though yes, he is technically bound together, he is bound to another fluorine, his oxidation state is 0. That is element. It is not combined to anything else. Whenever you have a monatomic ion, so it's a one atom ion, the charge is, so the oxidation state is what the charge is. So if we have chloride, the ion, the negative charge tells us we have a -1 oxidation state. Next up, oxygen. Almost always, I always start with oxygen. Oxygen is going to have a -2 charge, except in the rare case when you have a peroxide, in which case it has a -1. And that popped up out of order. There we go. There's the one that we wanted. Here's carbon dioxide. And this image here, oxygen, I'd start with oxygen. The oxidation state is -2. Since I have 2 oxygens, that means I have a total of -4. So that must mean that my carbon is +4. But I always start with oxygen. Oh boy, now they're popping up all over the place out of order. After I do my oxygens, the next element I look for is hydrogen. Hydrogen is going to have a +1 when it's in a covalent bond. So the example for that was ammonia, NH3. Again, you should first turn to hydrogen. I first turn to oxygen, but second I'll turn to hydrogen. We have hydrogen present. Hydrogen is almost always positive 1. Since there are 3 positive 1s, that's a total of plus 3. So that means my nitrogen has an oxidation state of negative 3. If you have neither oxygen nor hydrogen present, but you have a binary compound, then you choose the element that has the greatest electronegativity. Remember, fluorine, almost the top right. It's not a noble gas, but before we get to the noble gases, top right, fluorine has the greatest electronegativity, and it goes to the left and down from there. So choose your most electronegative atom, and it gets the oxidation state that's equal to its charge. So for example, here we have PCl3. Chlorine is the more electronegative atom. And oh, by the way, just kind of a helpful, friendly reminder, generally when elements are listed, we go left to right, least to most electronegative. So whichever element is listed second is usually going to be the one that has a lower electronegativity. So that could help you as well. So chlorine has a lower electronegativity. I know we normally say, oh, chlorine, I use in that halogen group, they all have -1. So, okay, we give them a -1. We might find phosphorus and say, oh, look at that, he's in the nitrogen family. We'd expect for him to be -3, but he's not. He's paired with chlorine. Chlorine has his -1. We have to get to 0. There's no net charge above this compound. So because I have 3 -1 oxidation state chlorides, phosphorus is going to have an oxidation state of +3 to cancel that out. So we've already kind of worked with this, but our next rule is that the sum of the oxidation states must equal 0 in a compound. If there's not a charge, if you're not working with a polyatomic ion, your charge is 0. So again, using rule 3 up here, I've got an oxygen. I'm going to assign it a -2 oxidation state. I've got 4 of them. So that's a total of -8 because of my oxygens. So in this compound here, N2O4, my nitrogen must cancel out the +8 because I have 2 of them. Each nitrogen has a +4 charge. And our final rule, when you have an ion, a polyatomic ion, well, your charge has to equal the charge of that ion. So here we have nitrite, NO3 -1. Well, again, my oxygens are going to have -2. Always start with oxygen. Rule 3. We have 3 of them. 3 times -2 is a total of -6. We have to get back to -1. We're not trying to go back to 0. So my 1 nitrogen must have an oxidation state of +5. Notice how +5 and -6 gives you a -1 overall charge. Well, that's where it comes from. Make sure at this time they don't balance out. We're working with an ion. Work on a few more examples here. Find the oxidation state for each of the following, or each element in the following compounds. K2Cr2O7. Again, I find oxygen. I go to him first. He's -2. Now you've got a couple of options on where to go next to balance out the K and the Cr. I would probably take a look at the polyatomic Cr07. You can find that on the back of your periodic table. He's in the middle column there. It's called dichromate. Do you see him? Notice the charge on dichromate is -2 overall. So that means that my oxygen, with his -2 charge and 7 of them, have a total of -14. But overall, we only have a -2 charge between these two. So because I must also then have +12, so +12 and -14 will give me my overall -2. My 2 chromes must each have a +6 charge. Why don't I have a charge up here after all? Well, I've got potassium and 2 of them with their +1 charges. So most of our alkali metals, like potassium, are going to have those positive 1 charges, so there they are, and this works out. Wow, a whole bunch more. So we have CO3, again, start with oxygen. Oxygen has a -2 oxidation state. There's 3 of them, so that's a total of -6. Because the overall compound has a -2 charge, I know that there must be 4 positives to get me back from -6 to -2. So that must mean carbon has the positive 4. There's only 1 carbon, so all positive 4s go to him. Manganic oxide. So Mn is going to have a positive 4 because oxygen has a -2, always -2 for oxygen. Times 2 gives me a total of -4. I don't have a charge, which means my manganese must carry all 4 of those positives. Positive 4. There we are. PCl5. Chlorine is the more electronegative element, so he gets his charge. His charge is -1. I have 5 of them. Phosphorus, in this case, must have a positive 5 oxidation state. Sulfur tetrafluoride. Fluoride is the most electronegative. Give him his -1. Because there are 4 of him, that must mean that sulfur has a positive 4 charge all by himself to cancel out those 4 negatively 1 charged elements. And sodium bicarbonate. Well, let's start with oxygen. It's going to have a -2. There's 3 of them. That's -6. If you want to, we can move to our hydrogen next. That'd be rule number 4, I believe. Hydrogen almost always has a positive 1. Again, we've got our options here. We could just find our bicarbonate on the back of the periodic table and notice that this whole thing, HCO3, has a -1 charge. Or we could move straight to sodium and say that's an alkali metal, and alkali metals are almost always positive 1. So there we are. Positive 1, and -6, because again, oxygen's -2, but there's 3 of them, leaves us with 4 positives right up the middle. So carbon must have that positive 4. So there's our carbon with his positive 4. Or again, if we had broken it down and looked at our bicarbonate by himself, you'll notice bicarbonate on the back of your periodic table has a -1 overall charge. If oxygen has a total of -6 and hydrogen has positive 1, we're going to need 4 more positives to bring the overall charge of the polyatomic ion back to -1. And that's where carbon gets his +4 from. +4 and +1 is +5, which gets us all the way back to 0, except for a -1 from our -6 oxygens. Hey, now that we're good with our oxidation states, let's try some basic redox reactions. Sodium reacts with chlorine, to form sodium chloride. Well, element by himself, 0. Element by himself, 0. Move over to the right. Sodium has a positive 1. Chloride has a -1. Who was oxidized? Who was reduced? Well, sodium lost an electron. Leo the lion. Loss of an electron is oxidation. Sodium was oxidized. But sodium is also the reducing agent. Sodium did the reducing of chloride. Chlorine is reduced. So again, gain of electron is reduction. So chlorine gained an electron. He went from 0 to -1. Electrons are negatively charged, so he gained an electron. Chlorine is reduced, but he's also the oxidizing agent. He oxidized sodium. He accepted the electron. Let's try another example. A little bit bigger problem here. Again, first step, assign your initial oxidation states. Well, carbon is -4 because I have 4 positively 1 charged hydrogens. Oxygen by himself is a 0. Move over to the right. Again, carbon is positive 4 because now he's paired with oxygen, who's negative 2 and 2 of them. So look at that. Carbon went from negative 4 to positive 4. Hydrogen stays at positive 1 and oxygen negative 2. Cancel out. There's our water, H2O. 2 positive 1s cancel out to negative 2. There we go. Okay, so we've got 3 atoms here, or elements, carbon, hydrogen, and oxygen. Not all of them changed. So not all of them were oxidized or reduced. Carbon is oxidized. Negative 4 to positive 4. He lost 8 electrons. So he was definitely oxidized. Now we don't break it up. Carbon, the atom, got broken up and was oxidized, but the reducing agent we keep together as the molecule. So CH4, methane gas, was the reducing agent. All right, how about who was reduced? Grrr! Gain of electrons is reduction. Oxygen went from 0 to negative 2. That's a gain of electrons. So oxygen was reduced. O2 is the oxidizing agent. Oh boy, got quite a few more here to do. Let's take a look. Well, zinc by himself would be a 0 and a positive 2 over here in the compound. So zinc was oxidized from 0 to positive 2. That's a loss of electrons. Leo, the lion, goes grr. But zinc was also the reducing agent. Again, whoever was oxidized is the reducing agent. Hydrogen ion was reduced. Here we have H plus and Cl negative. So H plus was reduced. HCl is the oxidizing agent. Why do I say H plus? Well, again, if we take a look at the compound HCl, hydrogen there does have a positive charge. But also think about it. Reduced means a gain of electron. If I were to say regular old atomic hydrogen was reduced, what would that mean? We're talking about an H gaining an electron. An H gaining a negative charge. You would have formed hydride, H negative, the ion. We didn't form hydride, H negative, the ion. H plus took the electron, was reduced, and became H2 with a 0 charge. So that's why we have to say H plus, hydrogen the ion, was reduced. Ooh, look at this. We got a polyatomic ion. 2 polyatomic ions. All right, let's take a look at what happened to this one. Not a redox. Must have been a trick question. So let's see. Oxygen, negative 2. That's a total of negative 14. Chrome, we have a total of negative 2 overall, so it must be positive 6 because I have to get to positive 12, and I've got 2 of them, so positive 6. Let's flip over here and take a look at chrome and oxygen. Again, oxygen, going to have a negative 2, so 4 times negative 2 is negative 8. I've only got 1 chrome paired, and I've got that negative 2 left over still. So once again, that chrome all by himself must have a positive 6. So nothing happened with chrome. Okay. Here's hydroxide, OH negative. Again, our hydrogen's going to have a positive 1, our oxygen a negative 2. That's why we have 1 negative left over. So nothing happened to our oxygens and nothing happened to our hydrogens. Hydrogen's plus 1 here and plus 1 over on this side. So not a redox. Nobody was oxidized. Nobody was reduced. Hey, interesting. Not saying you won't see that again. Very cool. All right, let's take a look at the decomposition. Copper chloride. So, the most electronegative element here is chloride. So we'll say negative 1. That means that we're working with copper plus 1. So copper plus 1, chloride negative 1. All right, now move over here. Wow, look at this. Chlorine, negative 2. Copper must now have a positive 2. So copper went from positive 1 to positive 2. That's a loss of electrons. But this is really interesting. We also have copper by himself. That would be a 0 overall charge. That's interesting. Well, that means that copper was both oxidized and reduced. Copper, the ion, copper plus 1 was oxidized. It lost an electron, became copper plus 2, but it also gained an electron. Copper plus 1 over here also went to copper, the element. So, wow, that's very interesting. Copper was both oxidized and reduced. We can say that copper chloride, or cuprous chloride, was the reducing agent, because both cuprous chloride took an electron and gained an electron. Gave an electron and gained an electron. So it was both the oxidizing agent and the reducing agent. Although we only have one reactant, so I guess it would have to be both. That's a fun problem. Okay, let's take a look at iron and copper 2 nitrate. Now, iron is oxidized. It goes from 0. Over here is paired with nitrate. Nitrate, the ion, would have -1. It has 2 of them, so iron now has a +2 charge. So iron, the element, was oxidized. Notice I don't have a charge up here. There is no charge with iron. It's all by himself, no charge. So iron is oxidized. That also makes iron the reducing agent. Now copper does get a charge. So we have copper 2+, and he goes from being a 2+ charge to copper with a 0 charge. It's now an element. That's a gain of electrons. Grrr. Gain of electrons. So copper 2+ goes to copper the element. Copper 2+ was reduced. Gained electrons. And our copper nitrate is the oxidizing agent. It oxidized, copper nitrate oxidized iron, the element. And finally, we have a halogen here. Chlorine gas reacts with potassium bromide to form bromine liquid, and potassium chloride, the salt. All right, well, we've got chlorine all by himself. That'd be a 0 on this chart side. But we'll move over here. Chlorine now has a -1. From 0 to -1, okay, it's a gain of electrons. Grrr, chlorine was reduced. Potassium has a +1 charge here. He's paired with bromine, which would have a -1 charge. And on the other side, potassium has a +1, because now paired with chloride, which has a -1. Guess what? That means potassium, K, didn't change. He started off +1, he ended at +1, neither oxidized nor reduced. How about bromine? Starts off with a -1, goes to its element. Elements have a 0 charge. -1 to 0. That's a loss of electrons. Bromine was oxidized. Leo the lion goes grr. Again, taking a look at the reducing agent, KBr, reduced chlorine. And chlorine, the gas, oxidized bromine. So chlorine, the gas, is our oxidizing agent. I did a couple of different problems with you there. Now it's your turn. Take a look. Practice. Get better.